I would like to start with saying that I appreciate this wonderful opportunity to participate in this great conference. Today, I would like to present my results on asymptotic properties of parameter estimators for mixed fractional Brownian motion. Those results were obtained in joint work with Professor Konstantin Radchenko. We consider ensure that everyone can see my screen. We consider the following mixed fractional Brownian motion with trend, which consists Wiener process W and a fractional Brownian motion B with index H capital with first index H in the interval from 0 to 1. And we consider fractional Brownian motion independent of Wiener process. Our goal is to estimate all four unknown parameters of this model: trend parameter, sigma, kappa, and unknown index, first index. I'd like to add the definition. Fractional Brownian motion is a centered Gaussian process with the following covariance structure. This process has parameter H, that belongs to the interval from 0 to 1, called the Hurst parameter or the Hurst index. In case of H equal to 0.5, this process just became the standard Wiener process, and for all other cases, there is a huge difference in between Wiener process in fractional Brownian is that the increments of fractional Brownian motion are not independent compared to the Wiener process, which has independent increments. Let us introduce the following notations. Here you can see four intermediate statistics. Those are not estimators for our parameters of interest, but those are intermediate estimators that will be used to construct our parameter of interest. Here you can see phi n, Cn, eta n, and delta n. Once we define these four statistics, we can state, based on the previously proved results in the work of Kukush et al., that those four estimators are strongly consistent estimators for the following parameters and their mathematical expectations. And by constructing those four estimators, then authors of this article use generalized method of moments by applying ergodic theorem to construct estimators for our parameters of interest, which are provided in the following slides. So you can here see four estimators for parameters theta, Hurst index, and sigma square, kappa square. As you can see, they are defined with the use of those four intermediate statistics. And additionally, here we denote logarithm with base 2 plus, which is logarithm of base 2 in case of x is positive and 0 otherwise. The strong consistency of this constructed estimator was proved in the work of Kukush et al., and we study their asymptotic properties. Firstly, we denote the following increment of our initial process x, which can be defined as theta h plus the increment delta z k, which is the sum of increments of Wiener process and fractional Brownian process. In this case, delta xk and delta zk are stationary Gaussian processes, and they have the following autocovariant function, rho tilde I, which can be defined using rho I, which is the autocovariance function for stationary sequence, which represent the increments of the fractional Brownian motion. That is, it is a well-studied sequence, which is known as fractional Gaussian noise. Defining this notation, we can state the following lemma, which will be needed for the further theorems. This lemma provides us some very important properties of sequences rho tilde and rho. It provides us some asymptotic approximation for rho I and the convergency for series built using rho I and rho tilde. What is important is that we can state that those series defined in this lemma converge only for h in interval from 0 to 0.5. In case of h higher than 0.5, the specified series do not converge. What is important to state is that the initial estimators that was proved to be consistent, they are consistent on an entire interval from 0 to 1, except of 0.5 where the model is undefined. Using this lemma, we can prove the next result. The vector of initially defined intermediate statistics is asymptotically normal, and the asymptotic covariance matrix of that vector can be presented explicitly, but with the use of the series defined in the previous lemma. As you can see here we define the asymptotic covariance matrix, and each element is presented on the next slide. Here you can see the definition of each of the diagonal elements, and on the next slide you can see that how each of the elements other than diagonal are defined. I will go back, and these series, unfortunately, their convergency limit cannot be explicitly defined, and in order to estimate those, we need to use some numerical methods. But the previously provided lemma proves that they converge, and we use them to prove the asymptotic normality of our intermediate statistics. And this previous theorem, theorem 3, allow us to prove our main result of asymptotic normality of constructed estimators for unknown parameters theta, h, kappa square, and sigma square, which is obtained from the previous lemma, previous theorem, and by applying the delta method to our transformation, which provide us the estimators constructed theta, h, kappa, and sigma from the intermediate statistics phi, c, eta, and theta. And the following result is presented on this slide. This matrix is actually bigger, but we use some additional notation to reduce its size. And once again, we impose this limitation on the Hurt index because in case of h higher than 0.5, convergency, the limits defined in the theorem 3 would not converge. Following obtaining those theoretical results, we investigate the behavior of our constructed estimators using Monte Carlo simulations. For each of multiple sets of parameters, we generate 1,000 trajectories, and for each of that trajectories, we construct our estimators. We estimate asymptotic covariance matrices defined in theorem 3 and 4 using those estimators of theta, h, kappa square, and sigma square. And in addition to that, for each of our statistics, we calculate the empirical means, empirical standard deviations, and square root of estimated asymptotic variance divided by n, and the cover probability for alpha equal to 5% based on estimator of asymptotic covariance matrix to show how accurate our estimation for the corresponding asymptotic covariance. The series, as was previously stated, those series, the convergence limits for those series cannot be explicitly defined, and we estimate them with some precision using numerical methods. For the purposes of this presentation, I present results with the precision of delta equal to the 10 in the power of -4. You can see how we were defining the series for first order, and on the next slide, you can see how we define the series of the second order, and each of those were separately estimated with the precision of delta equal to the 10 in the power of -4. These simulations were conducted for sample sizes of 2 in the power of 10, 12, 14, 16, 18, and 20 for set values of theta equal to 0.5, sigma equal to the 1.5, and kappa equal to the 2.5 for two the values of Hurst index, 0.2 and 0.4, as you will see in the next table. So, the final results. Here on this slide, you can see the results of our simulations for the estimator of Hurst index. As you can see, as expected, with the increase of the sample size, our cover probability approached the 95%, which is prove the accuracy of our estimation. And also, we can see that standard deviation and the square root of asymptotic variance estimator divided by n, they are quite close to one another, so we can also see that our estimation is quite accurate. What we also can see is that with increase of Hurst index, the accuracy of our estimator decrease, and it can be seen on this slide for the Hurst index. I will also go to the next slide. It's also much more clearly seen for the estimator of sigma square. You can see that we obtained the precision of 95% for the cover probability with Hurst index equal to 0.4, with the sample size of 2 in the power of 12. But for index Hurst index equal to 0.4, that was obtained only with the sample size of 2 in the power of 18. Additionally, on the next slide, you can compare the standard deviation of the kappa estimator. It's significantly higher than for the rest of estimators. And the reason for this is that estimator of kappa is the only one that have some statistics calculated in the denominator. And as a result, it's slightly more unstable compared to sigma, for example. And once again, it's less accurate with the higher values of Hurst index. And the same is applied for the estimator of the parameter theta. And its accuracy is closer to the estimator of Hurst index. In addition to that, we also estimated the cover probability for our intermediate statistics because we constructed their asymptotic covariance matrix. We also estimate this asymptotic covariance matrix in order to obtain the final estimator for our asymptotic covariance matrix of the theta, h, sigma, and kappa. And as you can see, it's much more accurate than the final asymptotic covariance matrix. And we assume that the reason for this is that we add an additional bias by applying the delta theorem and by multiplying by the additional matrices that is calculated using derivations. And that additionally provides us some additional validation of the accuracy of the theorem 3 and the formulas that we obtained for the estimation of asymptotic covariance matrix of these intermediate statistics. And finally, I would like to add that when we were conducting our simulations, we observed that quite significant percentage of our trajectories resulted in values of estimators that were not suitable to estimate asymptotic covariance matrix. By this, I mean that in some cases, our final estimators were non-evaluable, or the final estimated results for Hurst index were out of boundaries of interval from 0 to 0.5, which this cannot be used for estimating of asymptotic variance matrix, because in that case, the series is defined in theorem 3 would not converge. So if, for example, we conducted a simulation, we obtained some trajectory, we try to estimate Hurst index, and it's, for example, the estimation is 0.6. It cannot be used for to construct confidence intervals, because asymptotic covariance matrix defined in theorem 3 would just not converge. During my presentation, I was referring to the work of Cook-Stoll, where the strong consistency of the provided estimators were provided, and to our work with Professor Radchenko, where we prove the asymptotic normality of constructed estimators.
Thank you for a very nice presentation. I open the floor to questions, as usual.
Yes. Hello. Thank you for an interesting talk. I have two questions. First, whether there was some difference in the computational time for the different Hurst parameters. So maybe
actually,
some was slower or.
Yes, actually, yes, and it was significant. The higher the Hurst index and the closer it to the 0.5, the slower the asymptotic the series is defined in the theorem 3 converge, and as a result, the estimation took more time. And we are talking not about a few more seconds. For Hurst index equal to 0.2, it requires, for example, if I go up to this element diagonal element 2, 2, this one specific, it requires 300 elements of the sum to obtain the series with precision of 10 in the power of -4. In case if Hurst index is equal to 0.2. In case if Hurst index is, for example, equal to 0.45, it would require 20 or 15 millions. So it would require significantly more time. In terms of just estimating the unknown parameters, it would not have any impact. It would just took 0.4 seconds. But for estimating the asymptotic covariance matrix, it would require significantly more time.
Okay, thank you. And the second one was that in the table with the results, for some you saw that for a small amount of observations, the intervals were 100%, and then it got lower to the 95. But then I think for the variance, it got up from 74%. So why is the behavior different? If you have any idea or no?
Actually, we don't really have an answer to this question. And in case, for example, of the rand coefficient equal to 0, of theta equal to 0, the behavior is slightly different. For instance, as you can see, for example, this slide is a really good example. I think maybe that you were referring to this one, is that for the one value of Hurst parameter, we can see that cover probability decrease over time. And for another one, we can see that it increase over time. Unfortunately, we cannot explicitly identify why it's the case for now, but it's a really good question. Thank you.
Thank you. Any further question? I would also ask slightly similarly. I also noted similarly as Martina this disparity in the variance at 0.4. Are the results of simulations, perhaps I skipped this, based on any more formal mathematical properties of those estimators you mentioned, strong consistency, and maybe also what would happen at point precisely 0.5? Is there any explanation of the first index?
Well, exactly at the point 0.5, we will have that we would be able to estimate the actual parameters, estimators. There will be no problems, and we will not be able to estimate the asymptotic covariance matrix. Even if we will use true values, it will just tend to infinity. And as far as I know, based on this previous work that constructed these estimators, what might be the case what might be the case is that based on the previous experience, for the interval of 0.5 to 0.75, those estimators could still be asymptotically normal, but they would require a different coefficient for normalization. And in case of Hurst index higher than 0.75, they most likely would not be normal. They would converge to, I don't recall the exact name of that distribution, but that would not be normal distribution. And actually, in case of trend coefficient equal to 0, what is important is that this lemma and this theorem works on the interval from 0 to 0.75. And we cover this entire interval where we can guarantee that those estimators are asymptotically normal. And there are some sub-cases, specific cases that indicates that for the case of 0.75 to higher, asymptotic normality cannot be proved.
But maybe I misunderstood. So you are talking about the value of h, the Hurst index?
Yes.
So this holds also for h greater than 1/2?
Yes, asymptotic normality, yes, it holds for h value of greater than. So for this case, so what, let me open this lemma. So what we would have, our estimators would still work. And in case of trend coefficient equal, for example, to 0, then the assumptions would be much weaker. We can prove the asymptotic normality up to the Hurst index equal to 0.75.
Okay.
But in this case, the limits defined in this lemma, they would not converge. They would tend to infinity.